Number 8. The mass of an atom of 2311 Na, which is sodium, is 22.9898 AMU. Letter A. Calculate its binding energy per atom in millions of electron volts. Okie dokie. All right, so let's get this started, right? Letter A. We need to find that binding energy per atom. And they want it in expressed, in millions of electron volts. Okay, we got this. Now, anytime that we're talking about binding energy, and we're talking about an atom of some sort, right? In this case, they gave us a sodium atom. We know that we are probably doing probably one of the most famous formulas in all the land. Do you know a very famous formula, right? He was featured in the new movie Oppenheimer. I think for only a hot second, though. Our boy Einstein, the most famous formula in the world is, you guessed it, we're finally using it, E = mc squared. Now, this formula is more physics-based, right? But sometimes chemistry and physics will cross paths, and this chapter, it does cross paths with a little bit of physics. So, we want to find that energy value, and in this case, that's the binding energy. Now, when you find out this formula, this unit of energy is always going to be in joules. So just keep that in mind because somehow we have to change the joules to electron volts. Now the M is some type of mass, but if we're solving for a binding energy, we want the mass defect. Now the thing here is that there's going to be a discrepancy, right? Because things don't always, things aren't perfect, right? There's always a little bit of, not miscalculation, but just that in the real world, it doesn't really match up to theory. Now, the actual mass of the atom is showing to be 22.9898 AMUs. But our atom of sodium has its own protons, neutrons, and electrons, which we can calculate the theoretical mass. Now, we should see that, in theory, if it was a perfect world, that theoretical mass should match up perfectly with the mass that it's actually weighing at. But chances are it's not. So that's why this mass is representing the defect. The defect is the difference. So you could think defect, difference. It's the difference between, so literally subtraction. It's the subtraction between the theoretical value and what the actual mass is. And then C is a constant value. It's the speed of light, which will give the actual number 2.998 times 10 to the 8th meters per second. Now, if you wanted to do just 3, that's fine with me, but just want to kind of give you the exact or closer number for the speed of light. Okay, so we first have to find that mass defect. We already know the actual mass. Now we just need to find the theoretical mass in AMUs. Now that's going to come from knowing how many protons and neutrons and electrons we got from the sodium, right? So we have a 23 on top, we got 11 on the bottom, and it's sodium. Now always remember that the lower number, if they give you two numbers, right, in this case it's the 11, the lower number is always talking about the atomic number. Now the atomic number is the number of protons. So we already know that we have 11 protons. And since there's no charge in the upper right-hand corner, right, this atom has to be a neutral atom, which means that it has no charge. So all the positives from the protons, because protons are positive, will counteract with the negatives of the electrons. So if you have 11 protons, you must have 11 electrons. So we know the protons and electrons. Now we just need to find out the total number of neutrons. And keep in mind that the top number is the atomic mass. The atomic mass is your protons plus your neutrons. So it's got both of them in there. Neutrons. So if the 23 has protons and neutrons and the 11 only has the protons, what would I do with these two numbers to get just the neutrons? Yeah, we would subtract. So let's do that, right? 23 minus 11, if you got to use the calculator, that's fine with me, right? Just make sure that you get the right answer. This is a 2, it's a 12, right? 12. And then we could always just double check. 11 plus 12 is 23. Okay, so we got 11 protons, 12 neutrons, and 11 electrons. Now, I put over here the respective masses of each proton, neutron, and electron. So now we just have to multiply each one of these by their masses. So for a proton, one proton will weigh 1.0073 AMUs. So I just have to times it by 11. For the neutrons, each neutron weighs 1.0087 AMUs. And then the electrons are very, 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 very small. Keep in mind that protons and neutrons weigh way more than an electron. Might as well just throw that extra little piece in there for good measure. So let's see. 11 times 1.0073. Okay, so we get 11.0803 AMUs just from the protons. 12 times 1.0087. I get 12, maybe we'll do that in red, 12.1044 AMUs from the neutrons, and then 11 times 0.00055. Okay, I got 0.00605 AMUs. But now I have to compare it to the total AMUs that they gave us. So I'm just going to add these three values up. And we have the total mass of, we'll just take these three numbers, add them together, blah, plus, oh boy. But at least that was a cool color. This plus, oh, let's just clear it. Let's just redo this plus this plus that. There we go. Add it all up. Beautiful. And as I'm writing this down, take note as to there are two different values, the total masses. And there's your defect. There's going to be that some of them is lost. And that's what we have to solve for here. And just know that, mass can never be negative. So it's always the higher number minus the lower number. This is your theoretical number, so it should be higher. In actuality, you should always lose mass. So the mass defect here would be 23.19075, and I'm just going to subtract that from the 22.9898. So I'm going to take this number and subtract it from 22.9898. And that's the mass that's going in. But now, before we even do that, keep in mind that this is AMU. This formula, just like we said, is a physics-based formula, which means that we have to use all of the standard physics units. And the standard physics units for the standard physics unit for mass is kilograms, not AMU. So before we even do that, we have to convert AMU into kilograms. So now we're going back to good old dimensional analysis, right? We'll start with what we're given, 0.20095 AMU times that. Put the unit that you don't want on the opposite side. Always put your units first and then come back and put your numbers. And I did put over here that 1.6605 times 10 to the negative 27th kilograms equals 1 AMU. So the 1 goes on the bottom, and let me just move this over a little bit. And 1.6605 times 10 to the negative 27. AMUs cancel. And now we're going to be left with kilograms, which is beautiful. So we're going to take that number, times it by 1.6605 times 10 to the negative 27th. And that number looks good. Just making sure I didn't plug in anything incorrectly. So now we have 3.337 times 10 to the negative 28th. And that's in kilograms. And that's going to be the number here. 3.337 times 10 to the negative 28 kilograms. Okay, so pause the video if you need to. I just need to erase a couple of things here. Stuff that we don't need anymore. So the only thing that I will keep is just the total number of protons, neutrons, and electrons. We might need them, in the next part, but we'll get rid of that. And then I guess I will get rid of this conversion. Now we are ready. E equals mc squared. So E equals, that's a small e. E equals the mass, which we just said was 3.337 times 10 to the negative 28th. I'll use the whole number on the calculator. And then times by the 2.998 times 10 to the 8th. And that's squared. I could plug this all into the calculator in one shot, so that's what I'm going to do. But if you want to work, independently and do a couple steps in a couple steps, I guess, go for it. So we'll take this, times it by, whole parentheses, 2.998 times 10 to the 8th, close that up, square it. I'm just checking that I didn't plug in anything wrong. That looks good to me. And we got 2.999. So, maybe 3. But I guess we'll keep it that way. 2.999 times 10 to the negative 11th. And that's in joules. All right. Now, we got a binding energy, but it's in joules. We need it in millions of electron volts. Well, let's just convert it into electron volts first, and then we'll talk about the millions part. Down here is the conversion between electron volts, which is EV, and joules. Just two different forms of energy. So, times by a ratio. Put the unit you don't want on the opposite side. EV is going up on top. And now in this case, 1 electron volt is 1.602 times 10 to the negative 19th. Joules cancels out. And now we're doing a division. And I'm just going to pull this over just so that we have our new answer. So I'm going to take the full number divided by 1.602 times 10 to the negative 19th. All right, we're getting somewhere. 1.87 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 EVs. Now, let's see. What are we doing? We want millions of electron volts. So millions refers to 10 to the 6th, right? If you have $1 million, you get 6 zeros, after the 1. And 10 to the 6th for chemistry in your SI units, this refers to capital M, mega. Mega has the 10 to the 6th SI unit. And just know that 1 mega anything, right? So in this case, mega electron volt will equal 10 to the 6th electron volts. So that's the unit that we're going to be using to just convert. So what we're going to do is we're just going to use this conversion and convert from electron volts to mega electron volts. So all we have to do is just times by the ratio again. A lot of dimensional analysis. If you have another way of doing this other than dimensional analysis, go for it. We're just going to we'll move this over a little bit. Let me just clean this up. And then EV on the bottom, mega EVs up on top. EV. Gotta catch them all. For every 1 mega electron volts, you have 10 to the 6th electron volts. Electron volts get canceled. And then after this, there's one more thing to do. This divided by, we'll say, 2nd to the 6th. That's 10 to the 6th. And then there we go. Now, so we'll say 187. That's basically it, 187. Mega electron volts. But now they want it per atom. These are in per mole because in physics it's kilograms per mole because you're using the, quote unquote, the molar mass, which we know is grams per mole, but in this case it's kilograms per mole. So the last thing that we have to do, and I will take these conversions, I'll erase them. So just pause the video if you need to. Bye-bye. We're going to take those 187 mega electron volts, and we need to divide it by, because it's per, right? Per always means division. And it's per atom. Whose number always corresponds with the atom? You're right. It's Mr. Avocado, aka Mr. Avogadro, right? Avogadro's number is 6.022 times 10 to the 23rd. You could use 6.02, it doesn't really matter. And that's atoms. So, finally, we get this number. We'll take the whole number, divided by Avogadro's number to the 23rd. And now, there you go. Now, technically, if they do say per atom, it should be divided by Avogadro's number. If it was per mole, then I would have left it at this number. They, looking at this number versus this negative 22 gives me a little bit of a suspicion here. But they said per atom. And that's now going to be joules. Actually, no joules. Mega EVs per atom. And there you go. But if they secretly wanted, mega electron volts per mole, that would be the 187. Now, the next thing is letter B. So just pause the video if you need to. I'm going to get rid of this information because we don't need these conversions anymore. And now we're going to, maybe I will just put a little box here because we don't need that much room for B. Because we did all the hard work already. We just need to take that binding energy and find it for per nucleon. So, in essence, all we have to do is just translate the atom into nucleon. All right, so we're going to take the 3.109 times 10 to the negative 22nd mega electron volts. They didn't specify what unit of energy they wanted, so I'm just going to leave it in mega electron volt. And now times it by the ratio. We don't want atoms anymore, so that goes on the top. But we want nucleons. That goes on the bottom. Well, the question is, what is a nucleon? The nucleon are all your particles that are in the nucleus. So they are your protons and your neutrons. Keep in mind that the electrons are outside the nucleus in the atom. So, for every one whole atom of sodium, how many nucleons do you have? Yeah, 11 plus 12, right? It's the 23. That's the nucleons. So for every one atom, I'm just going to say that I have 23 nucleons. Atoms cancel out. And now you're just going to take this answer and divide it by 23. Similarly, if you wanted to take the 187 and divide it by 23, That's fine as well. And 1.35, we'll call it. 1.35 times 10 to the negative 23rd. And that's mega electron volts per nucleon. And that is the final answer. Yeehaw! Okay, so what'd you think? I hope this helped. Let me know in the comments. Thank you so much for viewing the video. Subscribe to the channel if you want to help us out. And if you want to become a member to the channel, you totally can. Check the membership out. We have 4 tiers, so one of them might suit your fancy. But thank you so much, and I hope you're having a great day. I'll talk to you soon. Okay, bye-bye.